Statistics is one of the most important fields for anyone doing software engineering, and it applies in just about every single domain. So of course, it is rarely a prerequisite for a computer science degree, because why teach something useful when you could be teaching linear algebra? When it is taught, it's often taught poorly with a focus on mathematics, which in this field can be quite daunting. As a result, most people end up learning just a few formulas and not learning the core concepts that underlie the mathematics. Before we continue, I should define what I believe statistics to be. It is taking a complex process, one that is often so complex it cannot be understood, and simplifying it to a model. Sometimes the model is ridiculously simple. So this example I have here is the iris flower. This is a well-known dataset in statistics called the iris dataset. A botanist, Edgar Anderson, went and measured iris flowers from a variety of different species. And from this, you can create a pretty good model for how large an iris flower is going to be based on the species. It's not a terribly complex model. It pretty much boils down to something like, on average, it is about 75 millimeters plus or minus 20. And that model tends to be fairly accurate, though not perfect. Now, understanding where these models aren't accurate and how accurate they truly are is an important part of statistics, but for now, let's look at the process that underlies this model. In this case, that process is insanely complex. There are a lot of factors, just think about it, in what determines how large a flower is going to be. So we've broken it down here. We have chlorophyll, and then you can break it down further. There's DNA, and you can break it down further. There's atoms, and you could probably break it down further if you wanted to into some kind of quantums or random quantum probabilities. All these things are going to have some effect on the size of that flower. How large a flower is going to be determined by the air that's around the flower, the dirt that's around the flower, how much rain the flower gets, when that rain arrives. And yet, this entire complex process can be summarized by this very simple model of 75 millimeters plus or minus 20. That is what statistics is, and that is where its power lies. So let's talk a little bit about what these models could be. If you're making video games, one thing you'll often want to stop is some kind of aimbot or cheater. Now, you can sometimes detect those by finding out how they interact with your code, but a lot of times to detect an aimbot, you need to have a statistical model for what it looks like to have a player playing your game. And then when an aimbot plays, you can see it behaves differently than a human being using the statistical model. There are statistical models for financial data, such as predicting the stock market, or more mundane things, such as trying to forecast revenue for your company. Robotics is going to use statistical models all over the place. In order to catch a ball, you have to have all kinds of models about how far you need to move, where you think you are in the world, and how much you should spin this motor to get it to go where you want it to go. All of these models are going to go into that robot. So what I'm going to do is create a series of videos, each one 5 minutes or less, that answers a short specific question. Each video will be part of a larger chain of videos that's answering a larger question. Eventually, I'd like to work these larger questions in some interesting questions like machine learning, building neural networks, support vector machines, and so on. I'm starting these videos with the assumption that you know nothing about statistics. You'll need some basic math understanding, but nothing too complex. I'll be skirting around any complex mathematics. If you want to follow the code samples, you'll need some basic understanding of code, but that's optional. So let's go ahead and take a look at the first larger question that we'll be tackling. That question is, what is the normal distribution and what makes it so normal? So if you don't understand what this chart is, that's fine. Hopefully you'll understand it more by the time we finish this question. And I've listed just a few of the things that we're going to go through here in the bottom, and I hope you stick around and catch the rest of the videos. Thank you.